Hey, what's up YouTube? So, back again. Alright, so we're on linear models still, the day 4 lesson. And what we're going to look at is this exponential moving average math. So this is the kind of Python code that we'll be trying to create here. But it's basically looking at some saved data. So like on a degree per minute. So let's say our optimal start algorithm is actually caching or saving our previous warm-up or cool-down histories in a degree per minute. We'll save that in a data structure in the code base. So this is exactly what the Tritium's optimal start block does not do. It only updates your previous degree per minute, which we kind of looked at briefly on the first video, decompiling the Java code base for that. But now we can kind of look at still the same linear model, but actually cache a few days worth of degree per minute data. And then we can actually take like a exponential moving average across that data to get a better degree per minute that's kind of averaged out maybe on the last 2 weeks, last 15 days, rather than only the previous run. So, and you should get some better performance. So on the Vibe code repo, if we go into the optimal start area, so in the Java code, we are actually, this is the same model 0, this linear degree per minute. And you can actually look at the Java code in here. So we actually, it looks kind of intimidating, but there's actually like a data structure for both heat and cool. So degree per minute will save a separate degree per minute for heating, a separate degree per minute for cooling. And it's all based off of if the zone is recovering for cooling or for heat. And those rates can be different. That's more of the mechanical engineering forte, that the degree per minute data is different because the load calculations are different for heating and cooling. So I just wanted to scroll down here in the Java code inside this block. So if we go all the way down into these helper functions, this is actually what we'll be doing here, just in Python, just kind of looking a little bit at this this same mathematical function here. So this is kind of our weighting factor, which I'll talk about a little bit later. But even though this is written in Java and gets compiled and I'm running it in program objects in the Niagara software, like we could actually study some of the theory in Python. So let me close out of this. I'm going to jump right into our daily lesson. All right, introduction to exponential moving average. So here we are. Concept and ideas is to tame the noise in daily measurement rates. Controllers can use an exponential moving average and kind of smooth out the data. It's used in a lot of places. We're just using it in optimal start, by the way. So this is basically our math code, which we just looked at before inside of the program objects, and we're using it for HVAC warm-up or cooling rates. So basically the new rate in degree per minute is the old rate plus this alpha parameter times the observed rate minus the old rate. Apply these concepts above using the formula and the algorithm provided. Refer to the mini examples why this matters. So here's basically our code. And these are adjustable parameters. I guess kind of like a PID. You know, you would have adjustable parameters and it'll affect it a little bit differently. So micro exercises. So starting with a rate of 0.2 degrees Fahrenheit. This works for metric units too, just having to use Fahrenheit because that's what my mind is used to viewing. 0.2 degrees per minute Fahrenheit. Update the exponential moving average with the observed rate 0.18, 0.22, and 0.16. Explain how these choices in alpha affect the balances between responsiveness and stability. Where else are exponential moving average used in engineering or finance? And create a simple Python file that performs the calculation for this lesson. Only use basic variables, arithmetic, and just a for loop. So, okay, here we go. So let's fire up VS Code. Actually, I have to get to the right folder on my computer. You can just fire up any Python file, any IDE, or even use idle, the built-in programming tool built into Python. Alright, so that was our code from yesterday. I'm going to delete that out. So let's get back to it. Alright, so here we go. Starting with a rate of 0.22. So I might just copy this right into Python code, even though it looks kind of funny. So this would be, I might even just copy this too. Hit the copy button in there. So might make it a little bit easier. So they want us to use an alpha of 0.2, and all right, so this is starting with a rate of 0.2 degrees per minute. So this would be our observed rate as 0.2, and then we can actually get a little fancy here. Maybe I'll try this. How, like the last lesson, we put Python into a little data structure called a list, kind of like an array. So I'm just gonna say old rates. So instead of just one old rate, we have old rates for plural. And then I can do another, like, even a little for loop here. Maybe we should turn this into a function too, like we did on the last one. We can do def compute new rate. And I think we could just say, oops, data. Sorry. Return new rate. All right, so we would want to put in, we would want to pass in observed rate. So we would want to pass these into the function, it looks like. Let's try old rate, alpha, and observed rate. All right, so we'll pass this into the function. So we could say this for rate in old rates, do a little for loop here. We could do, actually I might do this. For old rate in old rates, our new rate here will be what comes out of the function. Which we just have to call in. So we would just have to pass in old rate, alpha, and observed rate. Okay, so these are defined already. Even though they're the same names in the function, they don't have to be, but I just made them the same name. So this is also something in Python you don't have to do, but it's saying to make it a float with a precision of 2, or else you can use the round function, which I did yesterday. So let's just see if this works. Python math lesson. Okay, so maybe we'll do something just to make it a little easier to look at. If you do an empty print statement, it'll just separate these out a little bit. Okay, so our first rate, that's this guy right here. Our updated didn't change much. So as you can see, like we're for looping through these saved performances. So remember, these are degree per minute. These are the previous heating and warm-up cool-down performances that we recorded. So basically, when our optimal start block runs, it captures this data, which is really important. So optimal start, it'll capture time and basically the delta temperature, which we talked about yesterday, and it'll record this. So probably one of the most important things it records. And then we're just using an exponential moving average to compute, what would be the best rate to use now. So it's like basically it's just smoothing out the data. Is the only thing it's doing. So this could have been a day where it's kind of like medium cold, I don't know, 0.18 degrees per minute, or it's on some random day. Maybe the weather was just slightly colder outside, so that's why it took just a little bit longer. And then 0.16, it could have been, even milder weather outside, or different operating characteristics inside the building. So it's like these could be constantly changing depending on the dynamics, what's going on in the system, the loads, the weather. So that's what this code base is trying to do. It's just smoothing out the data. And the lesson wants us to experiment with these different alpha parameters just to see how it affects the smoothing process right here. So it's as we can see, it didn't affect it at all, basically. So neither did it down here very much. But I think we could even do so let's pretend that let's double this. We could even have an odd day, even some wild fluctuations in the data, and then it should actually help. Help smooth out, like what's going on in the system. So basically, when we're talking about the tritium's optimal start block, only uses the previous day's performance. So with this, we'd be getting a little bit better performance by smoothing out this data with this alpha parameter. I just want to run this once. So if we were using this for our optimal start logic with an alpha parameter of 0.2, we would come up with a little bit different degree per minute to use in our calculation to know when to start the HVAC a little bit early. We would try shooting for this based on smoothing out the data. So let's say if we update this to 0.5. which is actually smoothing it out a little bit more. I think it's just more aggressive as you go up. I think the value has to be between 0 and 1. So if we try a 0.9, and it's even more, this is most aggressive. So this is I'm using, I think, like a value of 0.5 in the linear model of the optimal start block that you can download from the Vibe Coder repository. So, which is kind of in the middle. I still don't really know like what the best parameters to set this would be. It's just something, it appears to be working from my point of view. But it's actually, maybe people could try it out themselves and then see what they notice as being, I have the best performance. But it could depend on where you're located too. So like where I am located in Wisconsin, it's we're having wild fluctuations in weather. So like this weekend, it'll be a high of 0 degrees Fahrenheit. And then right now on a Wednesday, it's 33 degrees Fahrenheit. So, and then by a week later, it'll be back up to 33 again. So like we're having like these wild fluctuations in weather. So winter weather. So like this, these would get very wild fluctuations in numbers too. In theory, because it would take longer to warm up the building, basically. So this alpha parameter could be different in like maybe a mild coastal climate versus upper Midwest USA. The weather is like a little bit more, fluctuates wildly. So I think that is it, guys. What what I wanted to talk about. And if you had like alpha setting of 1.0, there would be no smoothing at all. And it's kind of like a learning parameter, so it's like a learned rate. That's all I have for today. I think I'm just looking at some notes here. If there's anything else I wanted to talk about, I don't think so. I know like this lesson here I noticed. Create a simple for loop. Okay, we did that. So exponential moving average blends new observations with history, smoothing out random fluctuations in data, which we could definitely see in building warm up or cool downs. So, and then explain, I thought I saw something else in here. Where in other industries use exponential moving averages besides HVAC and I guess in any time series, anything. I'm trying to think of what could use. I know in moving averages are used sometimes in fault detection in HVAC to kind of smooth out the data. I don't know if it's an exponential moving average, but besides the HVAC industry, I'm actually kind of curious to know myself. So where else EMAs are used in engineering? I guess in smoothing out data, nothing's really coming to mind right now at the moment. And I don't really know much about the finance industry, but I think when someone would be making some kind of a judgment, which we're doing in building warm-up time, we kind of want to be somewhat of a smoothed out data and processes. So I don't know, I'd be curious if anyone watching this has any ideas. Feel free to post a comment. All right, guys, thank you for watching. See you on day 5.